So we have been looking at we have looked at two systems so far, MapReduce and Spark, and we have been looking at what is called batch computation. Right, so we have lots of data that is stored, and we have long running jobs that can take hours and days, and we want to run them in a fault tolerant manner, right, and scalable and whatnot. But this is not the only type of computation you may be interested in, right? So you may also be interested in streaming computation, right? So let us say we are doing some kind of real-time decision making, right? So someone did a credit card swipe and you want to figure out whether it was fraud or not, right? So you cannot do it in a batch computation system, right? You cannot say that I will store all the credit card transactions in last day and then I will run them in night and tomorrow I'll tell you whether it was a fraud, right? It's so we would like to tell whether it was fraud immediately when card was swiped. We also would like to do live analytics, right? So maybe people are tweeting and you want to show trending topics, right? What are people tweeting about, right? So let us say there was an earthquake and people start tweeting about earthquake. So trending topics will show that there was an earthquake, right? And someone can click on it and see what is going on. But again, if you do it in a batch computation system, people are no longer interested after 2 days, right? So things have to happen immediately. And there are many examples where you want to do streaming computation, like how many web page visitors I have right now, right? How many cars are passing this junction right now, right? So the additional concern that you have in streaming computation is freshness, right? So once data comes in, how quickly the computation gets out, right? How quickly the results of the computation gets out. And of course, we have all our old friends with us, fault tolerance, straggler mitigation, scalability, right? So we would like to also now support freshness while taking care of our old friends. So let us see why is this difficult, or what is the new challenge here, right? So let us say we know how to do MapReduce, right? So let us say I will just use the same system and try to tweak it for freshness, right? So let us say tweets are coming in. Maybe these are simple web servers which are getting tweets, and maybe they are tokenizing, right? So this is a mapper, simple mapper, right? Mapper is splitting tweets into keywords. Then we have aggregator, which is a reducer. Right, so the mapper will hash the keyword and send it to the appropriate aggregator, right? So all the A's are being sent to the higher aggregator, all the B's are being sent to the lower aggregator, right? And the aggregator is internally managing the count, right? So it knows that A is 43, this knows that B is 39, right? And every 1 second or so they are emitting the top 3 words, let us say, right? So this is one way you might implement trending topics in Twitter, right? So do you have a question? Okay. Right. Right, so this works. So what is the problem? This gives a pretty good freshness, because as soon as the tweets come in, they just flow through this pipeline and the words get counted, right? So we have pretty good freshness. So anyone sees any problems with this?
Each of the tokenizer, there is a one to many mapping.
No, but MapReduce also had the same. So any new issue here? Right. So the issue is this aggregator is now holding a state, right? If this aggregator goes down, right, and if I restart, so far our approach has been when a task fails, just restart, re-execute the task, right? So let us say this fails, so I restart, I say all the A's should now start going to this node, right? But we ended up losing the state, right? So A is reset to 0, right? And the word counts that we now produce will be incorrect, right? Because the state that this aggregator had is lost, right? So these are what are called stateful workers. So the workers had some state, right? And we don't want to lose them, because if we lose them, then we have a problem. So any thoughts what to do about this?
Let it store the state somewhere in some kind of a cluster or something.
Right. So the first idea is let's make things stateless, right? So we don't like state because state can be lost. So instead of writing to local memory, everyone as soon as they see a word, they will instead write to a local database. Instead write to a fault tolerant data store. Right. So this is good. But this will slow down the system, right? Every word, every update to every word is hitting the database, whereas previously it was only in the local memory, right? What was a memory update is now a remote database write. The another approach one can try is what are called replicated state machines. And we will look at them in more detail tomorrow. So let us say we are getting tweets, and this node was responsible for keeping the counts of A. So instead of keeping a single node, I will keep two nodes, right? And same here, right? And treat them as a single unit. Right. So these two nodes, these two servers are can be marked as primary and replicas. So primary is the one which is getting all the data from the upstream and also responding with data downstream. But it is also ensuring that the replica is caught up with it, right? So instead of keeping one common single database, every node is replicating its state on a replica, right? So the idea is once this primary goes down, we have not lost the state. This replica can become the new primary, right? And all the traffic starts going to the replica, right? That is sort of the hope.
But then does primary transfer data to replica very often? Because if not, then it becomes stale.
Very often. Every update has to be sent to replica. Yes. Right. So what happens if there are intermittent network failures between primary and replica? We will look at it tomorrow in more detail. But the general idea of replicated state machine is that you have primary and a bunch of replicas. So let us say they both think A is 41, right? When primary receives a request to update A, right, it first tells replica that hey, we need to update A. Then replica says okay, we are ready to update A, and then they both update A, right? So the computation should be can be seen as a state machine, right? We are going from one state to another. A is 41 to A is 42, but we are trying to replicate the state machine across different workers, right? So even if primary crashes, we hopefully have the state. So primary, so what do you think? Let us say primary and replica are two threads on the same CPU. Is that a good idea? What if they are on the same rack? Could have been even better, right? So the idea is that primary and replica should have uncorrelated failures, right? So if the power fails of primary, hopefully the replica is still alive, right? So they should have separate power source, separate network switches, separate whatnot, right? So that the yes, so the trade-off is if we put them very far away, let us say they are in two different data centers, then every update to A has to cross data centers, right? So this is a tricky problem in the application. But this is also not that great, right? Because first of all, we just doubled our resource requirement, right? So what could have been done with one server, now we are using two servers to do the same task. There is no straggler mitigation. This is actually going to run as quick as slower of the two replicas, right? So if let us say replica R is much slower than primary, primary is not allowed to leave R behind, right? So it should not happen that R thinks A is 42 and P knows that A is 53. This is not allowed, because if you do this and if primary crashes and when we go to replica, we will start seeing wrong counts, right? So the system can run at the rate of the slower replica, right? So this doesn't give us straggler mitigation. Okay, so one idea given by Spark in their paper called Spark Streaming is to break down batch computations into streaming, break down streaming computation into batch computation. Right, so tweets are coming in. So the idea is let's collect all the tweets for 1 second and run it like a batch computation, right? Then we collect all the tweets from the next 1 second and again run it as a batch computation, right? And we know how to do batch computation well. So let us look at a figure for this. Okay, so this is running a word count. So here this oval, this whole thing is a RDD, right? The blue things are the partitions, right? So every RDD has multiple partitions. What we are doing is for interval 0 to 1, we collect the inputs, right? We run it as a batch computation and we have a certain count, right? So what is the, so maybe this RDD contains that A is 41, this contains that B is 39, right? Then when we run the next interval, the value of A is transferred from the previous interval, right? So every node by itself again is stateless, right? So the node is not keeping any state. So here it can update A to 47 and B to 45, let us say, right? So the RDD partition doesn't need a state anymore. It only needs the inputs from this interval and some outputs from the previous interval, right? So the problem of state is gone, right? So our workers yet again become stateless, and when things crash, we can try to re-execute, right? So let us say this particular worker crashed, right? So all of its partitions are gone, right? So now I can recompute this, right, on a different worker. Maybe worker 2 is recomputing this, worker 3 can recompute this, right? Someone else can recompute a different partition. Then worker 2 continues to compute this, and maybe worker 3 computes this, right? So it also speeds up the recovery because you can recover in parallel, right? So these RDDs are recovered by a different worker, and these RDD partitions were recovered by a different worker, right? So the idea is basically treat streaming computation as mini batches, yeah. Yeah, so we assume that the stream is durable. So similar to how in MapReduce we were assuming our input file is durable. So stream is in a durable storage, right? So the input stream is in a durable storage. So do we like this? Is this great? So remember freshness, right? We added this discretization delay, right? So if a credit card was swiped at time 0, it has to wait all the way to 1 second before it can even start getting processed, and after that it will tell us whether it was fraud or not, right? So if you don't care about 0.5 second to 2 second delay, which is actually true for many use cases like Twitter's trending topics, it's okay if it is 2 seconds late. But if you really want your system to do real-time streaming, then we have added this unnecessary delay, right? Right. Okay, so we don't like this because we want to do real-time streaming. So, okay, so what is the plan? How to do real-time streaming while nodes have states, right? So we are back to square one, right? Nodes have states, these nodes have states, and we would like to do real-time streaming, and we would not like to have high cost and good performance. So the idea is, let's try to create checkpoints, right? So we will try to create checkpoints whenever we have state. So once we crash, we can recover back from the checkpoint, right? Okay, so any thoughts how to make these checkpoints?
So we can use the last method only, but we will do it like in continuous manner. But when we fail, we will go back to the last checkpoint. Let's say 1 second back, and then contain that data in the last second.
So the idea is, the rough idea that is being proposed is that the input stream is durable, right? That is our assumption, that we never lose the input stream. Then every 1 second we ask everyone to create checkpoint, right? So whatever state they have, they store it in some distributed storage, right? And when things crash, we recover back from the checkpoint, and we also rewind the stream, right? So we will have to reprocess the stream after the checkpoint. So how does this sound? Is this a good idea? Sounds like a good idea. But how to do this? How do we keep consistent checkpoints? So let us say, so let me play devil's advocate. Right, so let us say I had, actually I can make it even simpler. Right, so let us say this had some tweets coming in, and this has some tweets coming in. So maybe one idea is at every 1 second we announce a checkpoint event to everyone that hey, stop execute doing whatever you're doing, right? Create your checkpoints, right? So process the message that you're currently processing, create the checkpoint, let me know once you have created the checkpoint. Once everyone has created the checkpoint, then we resume the computation. Right, so this idea is called synchronous global checkpoint. Right, so we stop the entire computation, let everyone create their checkpoints, and then once everyone has done creating checkpoints, we restart. So the good thing is we should end up with consistent checkpoints. Right, when things crash, if the entire computation goes back to the checkpoint, we should come to a good state so that we'll reach the same final state if things had not crashed. But this is again has a problem with freshness, right? So let us say I was trying to do credit card transaction, just at that point system decided to create this checkpoint, right? So now my transaction has to wait for everyone to create the checkpoint, right? And then only then my transaction can be processed, right? So we would like to not pause the computation while creating this checkpoint.
So instead of keeping this one checkpoint, we can take like continuous 10-second checkpoint.
Right. So checkpoints are periodic. So we are keeping checkpoints every 10 seconds.
For the one checkpoint, we can keep 10 data points.
Okay.
Yeah, let's say from time t equal to 1 to t equal to 10. We are assuming that in this 10 second, at 1 second, all checkpoints will be synchronous. So we can use that timestamp to go back to our computation.
Say that again.
For each node, we will take checkpoint from time 1 to 10. But there may be there will be some overlap. We are assuming that there will be some overlap between the different intervals for all the nodes, and where all the nodes intersect, that is the point where all of them are synchronous, and we can go back to that point.
I don't fully understand, but let me try to rephrase. So I think the suggestion is that randomly create checkpoints. Every node randomly creates checkpoints.
Instead of taking just 1 second, we create a sequence of
Checkpoints.
then there will be a checkpoint for all the nodes where each of them has some data points.
Right, but the big killer is the consistency, right? So let us say this, here the A was 41 and B was 39. Right, so if you don't synchronize, then maybe this created checkpoint, right? And the stream was at this position. Then this B came along and it created a checkpoint at B equals 40. But then things crash, so you recover to this point and from this checkpoint. If you recover to this checkpoint, then your counts of B will become wrong, right? Because B node will double count this particular message. Right, so the issue is we don't want to stop the computation, yet we want to create consistent checkpoint so that even if I roll back to the checkpoint, I end up in a good state.
Can we add tokens to the input stream? Just that when those tokens fly through the workers play checkpoints at that time.
Very cool. Nice. So this is the idea implemented in a stream processing system called Flink, a very popular system, widely used in the industry. And the algorithm actually came a lot before Flink. It's called Chandy-Lamport algorithm for creating consistent checkpoints. So the idea is, so remember, we don't want to stop the computation, yet we want to create consistent checkpoint. And the definition of consistent checkpoint is, if I roll back to that point and if I go forward, I should end up in the same state such that no faults had happened, right? I should not end up in a different state. So the idea is to break the stream into pre-checkpoint messages and post-checkpoint messages, right? So the tweets are flying in, right? At some interval, let us say every 1 second, we want to checkpoint. So we can insert a special message into the input streams. Let's call them barriers. So everything after the barrier is a post-checkpoint message, and everything before a barrier is a pre-checkpoint message, right? So these are pre-checkpoint, these are post-checkpoint. And the guarantee we would want while creating the checkpoints is that everyone has processed the pre-checkpoint messages, all the pre-checkpoint messages, and none of the post-checkpoint messages, right? If everyone processes all the pre-checkpoint messages and then creates a checkpoint, and none of the post-checkpoint messages, then hopefully we'll end up in a consistent state. So let's see how this algorithm works. So the idea is every 1 second we are introducing these barriers in the input stream, then in all the input streams. Then what a node is doing is, it is going to keep processing, right, keep outputting. Then when it sees a barrier, it will create a checkpoint if it has a state, right, and then it will output a barrier on all its output streams, right, and then it will continue processing. So it is not stopping for anyone else. It will continue processing the red checkpoint, the red messages. So similarly, this guy outputs all the processes all the pre-checkpoint messages, outputs barrier on all the output channels, and then continues processing post-checkpoint messages. And then when this node sees a barrier on one of the input channel, because this now has multiple input channels, it has to wait for input barrier on all of its input channels. So once it sees barrier on all of its input channels, then it creates a checkpoint and outputs a barrier, and then continues processing post-checkpoint messages. So let's look at a concrete example of this. Any questions on this before we look at an example?
The barrier can get lost in between.
No. So we are assuming channels are reliable, right? So maybe we are using TCP in between, right? And TCP is ensuring a FIFO ordering, right? So TCP has sequence numbers, right? So pre-checkpoint remains pre-checkpoint, and things are not lost. Okay, so let's look at instantiation of this. Right, so let us say tweets are flying in, which are for simplicity just 1 character long, right? And the system decided to put a barrier at some random point. So these tokenizers don't have a state really, so they don't have anything to checkpoint. Right? So tokenizers output B on this channel, outputs A on this channel, then it sees this barrier. When it sees this barrier, it outputs barriers on both the channels, and then it sees A and outputs A on this channel. Then this tokenizer outputs 2 A's on this channel, sees a barrier, so it outputs barriers on all the channels, and then it outputs B. So let us say the starting state was 0 and 0 for both of our aggregators. So it will receive this first A and change the state to 1, right? So now it has received a barrier. So it will not process anything beyond the barrier until it sees barrier on all the channels. So then it sees this A, changes state to 2, sees another A, changes state to 3. Right? Now it has seen barrier on all the channels. So it will create a checkpoint A equals 3, and then it can continue processing beyond the barrier. Right? So it will output a barrier on its output channel and continues processing beyond the barrier. Similarly, B processes this message, changes to 1, right? Then it waits for barriers on both the channels. It puts B equals 1 in the checkpoint and continues with processing things that are post checkpoint. So now when the things crash, right, so let us say some node crashes, so we can restart our computation from the last checkpoint, right? So and make sure that the input stream is also at the point of the barriers, right? So now let us say new node starts processing A's, right? So it thinks that A is 3 and this is also rolled back, so it thinks B is 1, right? So they will process everything post checkpoint and end up with A is 4 and B is 2, right? Which is the correct final state, right? Because A is indeed 4 and B is indeed 2.
This can have congestion effect, like if some node is slow, and so like the stream will keep on collecting on that node, and other nodes are fast. So because of this, some issue can arise. There can be buffer overflow there, and the network can fail.
So if the network fails, then
Data packet can get lost. And
so everything is TCP in middle, right? So packet loss is already taken care of by TCP, right? FIFO ordering is already taken care of by TCP, right? So there is TCP, right? So we are assuming our channels give us reliable communication and our channels have FIFO ordering. Right? If the channels don't have FIFO ordering, then we'll have problems, right? Because post checkpoint messages may appear before the barrier, and then we might end up with weird situations, right? So even if you have unordered channels, put TCP on top of it to make it ordered for this algorithm to work. Right, so if B crashes before it made the checkpoint, but A has already made the checkpoint, so what happens? So basically we are introducing barriers at regular intervals, right? So every 1 second we are creating checkpoints. right? So if B was not able to checkpoint the latest moment in which it was supposed to checkpoint, this checkpoint is not considered complete. So we will instead roll back to a older checkpoint, right? So every 1 second we are creating checkpoints. Let us say for the latest checkpoint, latest set of barriers, B was not able to checkpoint and it crashes. So then we roll back to a even older checkpoint. Okay, so this, let's just play with this a little bit. So let's say I change this algorithm to say that I will checkpoint as soon as I see a barrier on one channel, right? I will not wait for barriers on all input channels, let us say, right? So then what happens? So the proposal is as soon as I receive a barrier on any of the channel, I will create a checkpoint and move forward. Let me clear things a little. Okay, so the proposal is, why do we have to wait for all the input channels before I create the checkpoint? As soon as I see a barrier, I'll create a checkpoint and move on, right? So we are just trying to see the subtlety in the algorithm, how it can create inconsistent checkpoints if we are not careful. So this initial state is still A. Let us say it receives this A and it makes a checkpoint as A. It sees A equals 1 and then it sees a barrier, so it immediately creates a checkpoint that A equals 1. Right? It did not wait for barrier to come from the other channel, right? And right, and this one created a checkpoint when it saw B equals to 1, right? So it kept it B equals to 1 in the checkpoint. So now when things crash, if we go back, if we go back in time to go to this barrier, right? Basically these two A's have been lost from our checkpoint, right? These two A's will never add up in the count because we started from a wrong position. So I hope this convinces you that the algorithm is doing something sensible. The correctness argument is simply that every node has processed all pre-checkpoint messages and none of the post-checkpoint messages, right? And therefore it produces consistent checkpoints, right? And the beauty of the algorithm is we didn't stop the computation, right? We didn't do a synchronous global checkpoint, everyone stops, right? So someone just locally creates checkpoints and resumes by throwing barriers on output channels, right? So I hope you appreciate this. It's quite interesting. Okay, any questions? So this is, by the way, implemented in Flink, right? So Flink claims that they support real-time streaming, and the reason they support real-time streaming is because of this algorithm, right? Okay, any questions? By the way, so we are taking a very cursory look. Streaming also has other issues. For instance, the issue of late data, right? So let us say I was reporting word counts every 5 minutes, but someone else's network was bad, so the data came late, right? So later than I have already told you the word count of last 5 minutes, but the data that arrived just now was actually originated 10 minutes ago. So how to deal with late data? right? So that is also an issue in streaming computation that we don't have in batch computation. Okay, so this concludes our discussion on computation. There are other systems, there are of course other systems, and they are also equally beautiful, right? But starting tomorrow, we'll start talking about storage, right? How to keep data even though disks are crashing. Thanks everyone.